we'll be talking about the traveling salesman problem. So, how an approximation algorithm can be written for the traveling salesman problem? Let us look into it. For that, let us understand what is a traveling salesman problem. So, it's a salesman who must travel between n cities. The order in which he visits the cities does not matter, but he has to visit each and every city during the trip and has to come back to the same place where he has started. So each city is connected to other cities by some mode of transport. And now the mode of transport doesn't really make sense anyway. The salesman wants to reduce the travel cost. He travels as slow as possible. See, I already said approximation algorithm will be mostly applicable to optimization problem. So here the constraint is he has to visit all the cities, come back to the same city, but the optimization here is the cost should be minimal. So that is the idea behind. So now, so it can be reduced to a weighted graph. So where each and every between the cities, if there is a mode of transport, how much it costs, that can be a weight. If there is a transport, that can be an edge, and then it should be a non-negative weights, because from going from one place to another place, it cannot have a negative weight. So that is one. So now what we need to do, we have to visit all the nodes and come back to the same node. So that means we should have a cycle. We should find a cycle which visit each at vertex exactly once. So the solution is the sum of the weights associated with the edge in the cycle, and the goal is to find a cycle whose total weight is minimum. Is that okay? The problem is clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Number? Is it clear? Shall I proceed?
Yes, ma'am.
Okay. So now you look at that way the graph has been created. So we have around 5 cities and almost all are connected, and you have the weights being associated. You are able to see, right? So now here I need to find a cycle which starts in any one of the vertices and then come back to the same vertex. So that is number one. Then that becomes a solution. Now then number two, that solution, whatever I say, should be made as minimal as possible. So now you can see the solution which is done in blue color. So this may be the one of the solution. So now what do we do? How do we go about finding the solution? So what we do is we use an algorithm called nearest addition algorithm. Actually, at the end of the algorithm, maybe you will be able to say you know this algorithm already. So what we do is start with a 2t, which initially includes 2 closest nodes. So u comma v, that belongs to v, that let us put that in yes. So what we do is among these edges, whichever is having the lowest cost, we choose that. Okay. So and then repeat till the number of nodes in S is equal to n. We'll repeat this because I have to start from a node, visit all the nodes, come back to the same place. That means I should have in my set of vertices all the n nodes. Okay. So now what we do is find a node Vj that belongs to V, and it should not belong to S. Already it should not exist in S. That is closest to S. So any one of the nodes, if it is closest to that, you choose that. Let Vj be the closest node that belongs to S, and Vk be the node that is following it. So now we can update again T by Vi, Vk already we had. So Vi, Vj, Vk and set S can be including that Vj that we have chosen. Is it okay? So what do? We start with the with an edge which has the lowest cost. So let that, it will be having starting and ending letters, those that let it belong to S. So now what we do is we choose the next node, I call it as Vj, which belongs to the set of nodes, which should not be already, it should not be the node which is in S. It should be closest to any one of the node that is in S. Like that we choose. And then we add that to our the set S. So now this node, whatever we have added, maybe with that we will be having three nodes. What are they? Vi, Vj, and Vk. So now now we'll have three nodes. So repeat again the same process again and again till you reach the number of elements in S is equal to the number of nodes in V also. So you can see how first this set is being added. Then from these two are in set S. Then what we have added, this is the nearest for any one of these two if you consider. So I add this. So that has been added in set S. So like this we keep on doing it till all the four nodes have been included. So all the edges that has been embed, that means that I have chosen for including that. Is that okay? Is it okay? Please answer.
Yes, ma'am.
Okay. So now let us proceed. Actually, this is what I said. This algorithm already you know. This is called the Prim's algorithm for finding the minimal cost spanning tree. This you have learned already, no? There are two algorithms for finding the minimum cost spanning tree. The first one is the Kruskal's algorithm. Second one is the Prim's algorithm. In Kruskal's algorithm, what we do in finding the spanning tree is we arrange the edges in ascending order of their weights. Yes, is there any echo, ma? Hello? Hello? Is there any echo?
No, ma'am.
No, you are able to
No,
hear?
ma'am.
Okay. So
Yes,
now,
ma'am. Yes, ma'am.
okay. So now the minimum cost spanning tree means there are two algorithms that are available. What I mean by minimal cost spanning tree, you should include all the vertices in the spanning tree with a minimal cost. So in Kruskal's algorithm, what we do is we arrange all the edges in the ascending order of their weights. We start with the lowest edge, then we'll try to add with those lowest what is the next lowest edge. Like that, we add. When we are adding the edge, it should not form a cycle. So finally, if we exhaust all the edges, or if we have all the nodes being connected will come out. That is your Kruskal's algorithm for finding the minimum cost spanning. In Prim's algorithm, what we do is we simply choose an edge which has got the minimal cost. Now, with these two, this is what we have done now. So, with these two, now you have two vertices. From these two vertices, where you can go with the minimal cost, that edge you add. So then the next edge you add. Like that, you keep on doing it till you have n vertices in your new set. So that's what here it explains. The algorithm is closely related to the Prim's MST algorithm. The edge is identified from an MST. The cost of the optimal tour is at least as cost as MST on the same input. Only thing is, from the last one, I have to come back to the first one. So that will be the new thing that I have included. So the cost of the tour on the first two nodes, Vi, Vj, is exactly 2 times Cij because I have only two I have to start, come back. So if I have only 2 nodes, the cost of visiting that is going to be 2 times Cij. Okay. So now we are having an iteration of Vj to be inserted in between Vi and Vj in the current tool. So that means I'm going to increase it by one more node being added. So Cij plus Cjk and minus of Cik, because that visit I need not have it, so that I can remove it. And I always assume this triangle inequality, that is Cjk is less than or equal to Cji plus Cik. What it means? Going from J to K is always smaller than going to J through an intermediate node. So that is what we call it as a triangle inequality. So that is being happening in the graph because we have only positive weights. If I have a negative weight, this is not true. Okay. So increase the cost in each iteration, and then hence we keep on doing this. So always it's going to be the final cost is twice the cost of that MS. So thus this algorithm is going to be a two-factor approximation algorithm. Is it okay? This is one solution. The simple words, if I have to explain, find the minimal cost spanning tree using prims and add an edge. Add an edge which joins the first and the last node that you have added to this tree. So that's all the algorithm is about. Is that okay? Is that okay?
Yes, ma'am.
Okay. Shall we move on to the next? Another way to look at the algorithm. This is called double tree algorithm. Compute the minimum cost spanning tree. Then replace each edge of MST by 2 copies of itself. So you will find a minimal cost spanning tree. In that you will add one more edge to, because going in and coming back. So for that you will do that. Find an Eulerian tour. What is an Eulerian tour? Eulerian tour is nothing but traveling through each and every edge in the graph. You have to come back to the same place. What again I'll repeat, an Eulerian tour is you have to start with the vertex. You have to go through each and every edge that is present in the graph and come back to the same place where you have started. Okay, that is called Eulerian tour or Eulerian cycle. What is a Hamiltonian cycle? What is a Hamiltonian cycle? Each node has to be visited and no repetition of the node. Here, what is the thing? Each edge
Each
has
edges.
edge. Yes, that is the difference. Actually, this Eulerian cycle is formed from the idea of the problem that they had earlier in Coinsberg problem. That's how this graph theory itself has started. So in that, they have identified that to any graph to have an Eulerian tour, the vertices should be of even degree. That was has been proved. If any vertex is of odd degree, you can never find an Eulerian tour. Okay, so that's why actually here in the previous step we have said very carefully, replace each edge by 2 copies of itself. So one to go, another one to come back. So that's why we are expanding the graph. Is it okay? Now, after making an Eulerian tour, shortcut the tour to get a Hamiltonian cycle. So then return the Hamiltonian cycle. So that let us look into that example. So here you have this graph, and then you find the minimal cost spanning tree. You can see, all the nodes are connected with a minimal cost. Is it right? So it can be prims or it can be crystals. That's left to you. But the only thing is you need MSC. After that, what is the next step? After finding that, you have to repeat each edge. So 120 to go in, another 20 to come out. So you can see, nice column. Yes. Okay. So now what I have to do? Now this is in this I have to find an Eulerian cycle. Okay. So now you can see whether it is you are starting with C1, right? From C1 to C3, right? C3 to 10, 10. Okay. C1 to C3, and then C3 to C4, C4 to C5. So like that you go till you reach C1. So I started with C1, ended with C1, and all the edges have been visited. Is it right? One. So how many you have got? 1, 2, 3, 4, 5, 6, 7, 8, 9. That means 8 edges I have visited. That is being done, right? All 8 edges have been visited. So now what I do is, from this I have to find a Hamiltonian cycle, right? Hamiltonian cycle, I have to visit each and every vertex once and come back to the same place where I have started. So you have started C1, C3, C4, then C5, C2, come back to C1. Yes, the cycle is very obvious, right? Yes. This is what actually is going to be a solution for traveling salesman problem. So this may have a cost. I cannot say 100% minimal. It's very close to the minimal cost. Is that okay? Is that okay? You are able to hear? My connection says unstable. Hello? Hello?
Yes, ma'am.
You are able to hear? You have followed what it is, how we have given the solution?
Yes, ma'am.
What did we do? Tell me. First step, find the...
Minimum cost money.
Yes, good. Second step,
Double the edges.
double the edges.
Edges.
Third step, find the Eulerian cycle. Yeah, what I mean by Eulerian cycle, you have to visit each and every edge and come back to the same place, right? You should not visit the edge twice. So that's why actually we are doubling the, in the spanning tree, we are doubling all the edges. So then now, then last step?
Hamiltonian cycle.
Find the Hamiltonian cycle. That's it. So then we are able to get a cycle which starts in a vertex and come back to the same place, and we visit all the nodes. And the only objective whether it is met or not, I don't know, but I know for sure I have found an approximate solution because I have started with